So hi again. We've recently covered the nth roots of unity. Well, it was actually the 5/5 roots of unity in another video. And to be realistic about this, a further maths paper probably wouldn't be so kind. It's more likely that it will ask you for the, for example, the 5/5 roots of 1+i, where 1+i is no longer unity, but actually a number on the complex plane. So if I were to sketch this on my real imaginary axes, I know it would be one along in the real and one up in the imaginary, and I'd end up with pi by 4 as my argument, and my modulus is going to be equal to 1 squared plus 1 squared rooted, so root 2. So I can rewrite 1+i as root 2 brackets cos pi by 4, because we're going to be using de Moivre's theorem, so this is a more convenient way of showing the complex number, I sine pi by 4. So we're going to be working with that form, the trig form of z. Now we want to find the roots, or the 5/5 roots of z. So I'm going to move down here because I'm going to run out of room pretty quickly. So we know that z to the 5 is equal to root 2 brackets. Now there's going to be 5 equally distributed roots around the complex plane. So we're going to, as before, add multiples of 2 pi, integer multiples. So it becomes cos pi by 4 plus 2n pi plus I sine pi by 4 plus 2n pi. Okay, now you can see why I had to move down because it's expanded quite a lot, and this actually within the brackets can cause a few issues. So what I'm going to do before I even start taking the 5th root is a nice little fix. I'm going to say root 2 is 2 to the half because I'm going to be having to multiply that shortly. But I'm going to combine this into one fraction. So I'm going to end up with pi plus, this is 8n pi over 4, so it'd be 8n pi all over 4. I'm sure I did this in the last video. Okay, not forgetting my cos, kind of important. Pi plus 8n pi upon 4 plus I sine, and then once again pi plus 8n pi all over 4. I just kind of need to neaten that up. Pi plus 8n pi all over 4. So what we can now do is we can take the 5th root of both sides and then apply de Moivre's theorem as before. So z is going to be equal to, and this is why I chose to write root 2 as 2 to the half. I'm going to multiply that by 1 over 5, so I get 2 to the 10th. Okay, and within here, again, so I'm going to take the 5th power of all of this, and save it having to write it out twice, I'm going to multiply it as de Moivre theorem goes. I'm going to multiply each of these angles or arguments inside the brackets by 1 over 5. So I end up with cos pi plus 8n pi, and this is why it was convenient to put the fraction over 4 beforehand. So now it becomes 4 times 5 over 20 plus I sine pi plus 8n pi all over 20. Okay, so that is our generic or general form of the nth roots of, or the 5/5 roots of 1+i. Now what remains to be done is set n is equal to 0 for our principal solution, 1, 2, 3, and 4. I'm only going to sub one value in because you will be expected to cover all 5 within an exam. So just for argument's sake, excuse the pun, I'm going to set n equals 1. So we end up with our, so it will be our second one, or z1, because z0 will be our first, and we end up with 2 to the 10th and cos. So here I'm going to put 1 in place of n, so I end up with 8 pi plus pi, so it becomes 9 pi upon 20 plus I sine, and then once again 9 pi upon 20. So that is our second fifth root of our complex number 1 plus I. Please be aware that when you start moving on to n equals 3, n equals 4, you start actually going into the bottom region of the Argand diagram, and if you are expected to quote the argument between negative pi and pi, then you will have to adjust accordingly. Okay, and I will do another video on this. Okay, wasn't too bad. In fact, it was an exam question I went through with some of my students last year. Thank you.